Okay, so welcome back to another video. So in today's video we have the following definite integral from 0 to 1/2. We got gamma functions, so gamma 1 plus x times gamma 1 minus x divided by gamma of 1/2 plus x, and then multiply by gamma of 1/2 minus x dx. And we're going to be using Euler's reflection formula as part of our little definition, and then rewrite this integral. Same thing for the denominator, but that's going to be like, that's a new formula that's never been seen in this video before. And as we continue on going through this whole process of integrating this integrand, we're actually going to take a little bit of a different creative approach that I don't think it's ever been mentioned in this channel at all, so that's probably exciting. And also, if you want to see the whole Euler's reflection formula proof / derivation, I can leave that in the link in the description below that you guys can check for yourself. Other than that, I have no other comments to add, so we can actually start off with the definition. The definition for, of course, we're going to say that Euler's reflection formula is that gamma of x multiplied by gamma of 1 minus x, that's simply just equal to pi divided by sine of pi times x. And then, of course, we're going to be introducing the new formula that's listed in the denominator, that gamma 1/2 plus x, and then times gamma of 1/2 minus x, simply is just equal to pi divided by cosine of pi x. Now, the proof is actually really simple. You could just let, for example, x equals 1/2 plus n, and if you substitute this back in for x, you're going to get that for the denominator is sine divided by pi times 1/2 minus x, which, if you actually can use the following trig identity, is actually equal to, well, we write this as pi times secant of pi n, and then just rewrite that secant as 1 over cosine. You get this formula over here. We just replace with x, for example. We're just it's basically just a little dummy variable I just replaced, but simply that proof follows from that substitution. So from there, let's actually divide these two. So we have gamma x times gamma of 1 minus x, and then divide by gamma 1/2 plus x, gamma 1/2 minus x. Simply it's just equal to, so the pi's will cancel. We flip the reciprocal, so it'll be cosine of pi x divided by sine of pi x, and of course that will be equal to just cotangent of pi x. Now what I can do is, how about to manipulate some things so that we match our integrand, let's actually multiply x to both sides of the equation. So we have gamma x, then gamma minus, gamma of 1 minus x. And of course the denominator is still here. Then on the right hand side, that'd be x times cotangent of pi x, right? So here's the little identity from here. X times gamma of x, we know from the properties that's just actually equal to just gamma of 1 plus x. So I can just replace this. And then of course the right hand side still stays the same. But would you look, this is exactly our integrand right here. So I can actually just replace this integrand with the new integrand, that it's now the integral of x times cotangent of pi x. So now we have the new integral over here. Really the bounds stay the same, we haven't really done much. So x times cotangent of pi x dx. Okay, so there's probably many ways to integrate this, but as I said, we're going to actually take a little bit of a creative approach here. So what I can do is that I can actually rewrite cotangent pi x dx as a new differential. So really it's the derivative of some function that's going to equal this. So if I were to take the antiderivative of cotangent pi x, for example, I'm just skipping the steps here, really that's actually easy to show that simply just by using u-substitution. So we have that this is just x, and then multiply with the d as for the differential of the natural log of sine of pi x, and then we divide this by x. Still an infinitesimal, so we can actually rewrite this. Even if you actually take the derivative, you're going to get the same thing here, and then multiply with that differential dx so that it matches. So that's nice, and it's actually pretty neat. And now from here, what I can do is we're actually going to perform integration by parts. So we want to choose something that's easy to differentiate and easy to integrate. So of course the obvious choice being that x is the easiest to differentiate. So du is equal to dx. And then we have that dv is equal to d of ln of sine of pi x, and then divide by x. And then if you were to integrate that, you're just going to get the same thing that's in the parentheses, ln of sine of pi x, and then divide by x. And now from here, you just, all you got to do is just perform the, this is actually supposed to be a, that's actually supposed to be pi over here, I bet. Pi, and then right here is pi. Okay, so now we can actually just use our integration by parts, multiply u times v, and then integrate v du. Let's see, so we have x, then ln of sine of pi x, then divide this by pi, and then of course we're integrating this from 1/2 to 0. We'll get to that in a sec. And then I can factor out the 1 over pi, and then we have our integral, then that's from 0 to 1/2 of the natural log of sine of pi x dx. So now you can actually see that if I were to plug 1/2 into this, if I plug our bounds for 1/2, so let's see, if I plug 0, whole thing becomes 0. So if I were to plug 1/2, so this is sine of pi over 2, that's actually going to just go to 0. So that means this term over here actually just equals 0. So now the only thing we have left is we just need to evaluate our second term, which is minus 1/2 or minus 1 over pi, and then the integral from 0 to 1/2 of the natural log of sine of pi x dx. This is simple that what I can do is I can actually just do u-substitution. So I'll let u equals pi over x, then du is equal to just pi dx. And then I can actually just divide the 1 pi. So over here I'll just have 1 divided by pi squared, since I just factor out the pi from out here and divide by that. Then we calculate our new bound. So if I plug pi for here, or excuse me, if I plug 0 for x over here, this is just going to be 0. And if I plug 1/2 over here, this is just pi over 2. And then we have the natural log of sine of u. Okay, so integrating this, the integral from ln of sine of u du of 0 to pi over 2, it's a lot complicated than you'd think. I actually did cover a video where I integrate this same integral, but except the bounds are from 0 to pi over 4. And using that method is actually not exactly the same as proving the same method from here with a different bound. So it was basically you would actually use a substitution and then use your properties of logarithms to help evaluate this whole integral. I'm just going to skip that process. Probably one day in the future I'll probably make a video proving this same integral over here. So we'll just hope. But what the value comes down to is that, so I have negative 1 over pi squared. That's just from here. And then we multiply this. So this integral is actually just equal to negative pi divided by 2, and then the natural log of 2. And then that's pretty much it. Just distribute everything in. So negatives cancel, and then one of the pi's cancel. So now really the last thing is that it's just, we have that this is just 1/2, or rather it's actually the natural log of 2 and then divided by 2 pi. Or if you want to be fancy with it, you could say that this is just the natural log of the square root of 2 and then divided by pi, like so. And there we have it, like so. So yeah, probably one day in the future I'll probably prove this integral over here. Like I said, I did, if you want to see that other video where I proved this same integral but with a different bounds, I'll also leave that in the link in the description. But it's not exactly the same thing as a way of trying to perform the evaluation likewise. So just keep that in mind. So yeah, that's pretty cool if you ask me.